All right, welcome. Today, we're going to dive deep, really deep, into the heart of your computer chip. We're talking about a place where precision is measured in single atoms, and where one tiny mistake, well, it means disaster. We're going to pull back the curtain on a hidden process that is, no joke, absolutely critical to every single piece of modern electronics.
So let me just start with a question for you. When you picture a computer chip, what comes to mind? Probably silicon, right? Maybe some exotic metals. But what if I told you that one of the most important materials, the thing that acts as a gatekeeper for every single transistor, is something way, way more common?
Yep, it's glass. Specifically, it's an ultra-pure, unbelievably thin layer of silicon dioxide, SiO2. This perfect little layer of glass is an insulator, and it controls the flow of electrons that are, the very lifeblood of our digital world. Without it, your phone, your computer, none of it would work, period.
So the big question is, how do you even create this impossibly perfect layer of glass on a silicon wafer? You don't just pour it on. No. They grow it, atom by atom. It's a process that's way more like high-tech baking than it is manufacturing. And this process has a name, thermal oxidation. To put it simply, it's a very, very carefully controlled chemical reaction. You take a perfectly pure silicon wafer, you stick it in a crazy hot furnace, and you expose it to some very specific gases. The silicon on the surface then reacts with that gas and literally transforms into a perfect layer of silicon dioxide. Now, here's where it gets really interesting. Engineers basically have two main recipes they can choose from. It's not a one-size-fits-all kind of deal. They can go with either dry oxidation or wet oxidation, and believe me, the choice they make has a huge impact on the final chip. Okay, so first up, we have dry oxidation. You should think of this as the perfectionist's method, the artist's touch, It uses pure oxygen gas, and the reaction is really slow. But that slowness, that's its superpower. It produces this incredibly high-quality, super dense, and just beautifully uniform layer of glass. This is exactly what you need for the most critical part of a transistor, that ultra-thin layer called the gate oxide. And then, on the other hand, you've got wet oxidation. This method uses water vapor. We're basically talking about high-temperature steam. And this reaction is way faster. So what's the catch? Well, the glass layer it creates is a little less dense, a bit lower in quality. But that's okay. It's perfect for when you just need a thick layer of insulation, and you need it fast, like for the field oxide that separates different parts of the chip. So, it all comes down to this trade-off, which you can see laid out perfectly here. Do you need perfection, or do you need speed? For a thin, flawless gate oxide, you choose the slow and steady dry method. For a thick, general-purpose insulation layer, you go with the fast, wet method. The amazing part is, engineers actually use both recipes on the very same chip for different jobs. So we've talked about the chemistry, the recipes. Now let's talk about the kitchen itself. This atomic level cooking happens inside these massive, incredibly precise ovens called furnaces. And just like the recipes, the design of the furnace has evolved in a really dramatic way. Now this is the classic design, the horizontal furnace. See, the quartz tube where all the magic happens is laid down flat. For a long, long time, this was the standard, especially for smaller, like 6-inch wafers. But it had some problems. Gravity could cause issues, and getting the temperature and gas flow to be perfectly even across all the wafers, that was a serious challenge. And this right here is the brilliant solution, the vertical furnace. Just by standing the tube upright, engineers solved a bunch of problems all at once. For one, it saves a ton of precious, super expensive cleanroom floor space. It also lets you use robotic arms for fully automated loading, which cuts way down on pesky particle contamination. But the best part? The boat holding the wafers can actually rotate during the process, which guarantees every single wafer gets an incredibly uniform blast of heat and gas. This thing is the workhorse for all modern 8 and 12-inch wafers. Yeah, this comparison makes it crystal clear why the whole industry made the switch. For these massive, automated factories pumping out today's advanced chips, the vertical furnace's high uniformity, its smaller footprint, and its full automation just make it the obvious winner. Okay, so we've got the right recipe, we've got the right oven, but there is one more variable that is more critical than anything else. One factor where the tiniest little error means complete and total failure. We are talking about the precision war of temperature. Just look at this number, plus or minus half a degree Celsius. Now, get this.
Inside a furnace that's running at over 1,000 degrees Celsius, that's hot enough to melt aluminum, by the way, the temperature across a huge batch of hundreds of wafers cannot vary by more than that tiny amount. Let that sink in for a second. The level of control needed is it's absolutely mind-boggling.
So, what's the big deal? I mean, what really happens if the temperature is off by just 1 or 2 degrees? The consequences, well, they aren't just minor imperfections, they are catastrophic. If the temperature is uneven, the oxide layer grows at different rates, right? So you get thin spots and thick spots. The thermal stress can literally warp the silicon wafer or create microscopic cracks. It can even introduce defects into the perfect silicon crystal structure itself, causing something called dislocations. These things make transistors leak current and fail. A single one of these defects can ruin an entire chip. And as this quote makes really clear, this level of precision isn't just some nice-to-have goal. It is an absolute, non-negotiable requirement. The reliability of every single device we depend on hinges on maintaining this perfect thermal stability, second by second in factories that are running 24/7. So when you put it all together, you realize that growing a simple layer of glass is anything but simple. It's this incredible dance of precise chemistry, advanced mechanical engineering, and just an obsessive level of temperature control. It's not manufacturing, it really is atomic scale orchestration. So the next time you pick up your smartphone or open your laptop, just take a second. Think about the journey its components took. Think about that perfectly controlled 1,000-degree fire inside a vertical furnace, rotating slowly, meticulously growing a flawless layer of glass, one single atom at a time, to make its silicon brain possible. It's a hidden world of incredible precision that powers our own. Thanks for tuning in.